Find the equilibrium solutions for the model we wrote for the amount of sugar. So I've rewritten the model down here. Equilibrium solutions mean the amount of sugar is not changing, which means that the derivative is 0. So we replace ds dt with 0 and solve for s. So I'm going to subtract 20 from both sides and then divide both sides by negative 0.03, and you get s is 666 2/3. Use separation of variables to find an analytic solution to the differential equation dy dt equals t plus 1 over y to the fourth plus 1. Once you've integrated, don't bother solving for y. That is often the hardest part, so that should make things a little easier. Okay, so I have dy dt equals t plus 1 over y to the fourth plus 1. I need all of my t's, including the dt, on one side, and all of my y's, including the dy, on the other. So this is sort of just a cross multiplication situation. So I have y to the fourth plus 1 dy equals t plus 1 dt. And then we integrate both sides. So we have y to the fifth over 5 plus y. Technically there's a plus c here, but I'm going to just smush all of my plus c's into one constant term on the other side of the equation. Equals t squared over 2 plus t plus c. And again, we don't have to solve for y, so we just circle this. It's an implicitly defined function. Okay, number 3. For each differential equation, if it can be solved using separation of variables, do so. If not, say so. So for this first one, I can separate it by factoring out a y. And then I'm going to get all my y's on one side, t's on the other. So I have 1 over y dy equals 1 plus t dt. Integrate both sides. ln y equals t plus t squared over 2 plus c. And then we raise e to both sides to solve for y. So y equals e to the t plus 1/2 t squared plus c. And then I'm going to do this little trick that we're going to see many, many times this semester, where I'm going to say, oh, look at all of these terms in the exponent. They're being added together. I'm going to do sort of the reverse of a rule that we use frequently that says if you're multiplying like bases, you add the exponents. So I've got exponents being added here. So I'm going to rewrite this as e to the 1/2 t squared plus t times e to the c. And then e to the c is just a new arbitrary constant. So this is going to be c e to the 1/2 t squared plus t. Okay, part B here is not separable. There's no way to break up the y and the t. They're not, there's no way to have one factor that has all y's and one factor that has all t's. Use separation of variables to find an analytic solution to each of the following initial value problems. So the hint is first solve using separation of variables, then use the initial value. Okay, so this is separable. I can get my e to the y onto the other side. This would become, it's like I'm dividing both sides by e to the negative y. So you have 1 over e to the negative y dy equals t squared dt. But 1 over e to the negative y is the same thing as e to the positive y. And then integrate both sides. The integral of e to the y is e to the y. Integral of t squared is t cubed over 3 plus c. And I want to get that y. I'm solving for that y, so I'm going to take the ln of both sides. The ln of e to the y equals the ln of t cubed over 3 plus c. And the ln of e to the y is y. So y equals the ln of t cubed over 3 plus c. And remember, you can't, quote unquote, distribute the ln. There's no way to simplify the ln of a plus b. So we have to just leave it like that. But I can solve for c by using the initial condition, y of 0 equals 2. So y of 0 equals, now I'm going to put a 0 in for t, and I get the ln of c equals 2. And to solve for c, I take e to both sides. So c equals e squared. So my final solution would be y equals, I'm just rewriting this equation, but replacing the c. Y equals the ln of t cubed over 3 plus e squared. Okay, part B. That is separable. My y to the 4th needs to move to the other side. So I'm going to do 1 over y to the 4th dy equals t times the square root of 1 plus 3t squared dt. Integrate, integrate. So 1 over y to the 4th, I could rewrite that as the integral of y to the negative 4 dy, and then it's just a power rule problem. And then on the right, I'm going to do a u substitution where u is 1 plus 3t squared, which means du is 6t dt, which means dt is du over 6t. So this is going to become the integral of t times u to the 1/2 times dt, which is du over 6t. My t's cancel. So the integral of y to the negative 4th dy, I add 1 to the exponent and divide by the new exponent. And then the integral of u to the 1/2, well, I have a 1/6 out front. And then the integral, I add 1 to the exponent, divide by the new exponent of 3/2, which is the same thing as multiplying by 2/3, plus c. And then I got to plug in my u. So y to the negative 3, say negative 1/3, y to the negative 3 equals 1/9. That's 1/6 times 2/3, 1/9. U to the 3/2, u was 1 plus 3t squared to the 3/2 plus c. Then I just have to solve for y. So first I'm going to multiply both sides by negative 3. So I get y to the negative 3. In fact, I'm going to rewrite that as 1 over y cubed equals negative 1/3 times 1 plus 3t squared to the 3/2 plus c. And then, okay, so I'm running out of room here on this page, so I'm going to go to a new slide and finish this up. 1 over y cubed equals negative 1/3 times 1 plus 3t squared to the 3/2 plus c. I rewrote the initial condition that was given. So I'm trying to solve this for y. So I'm going to cross multiply here, and I'm going to get y cubed equals 1 over negative 1/3 times 1 plus 3t squared to the 3/2 plus c. And now I just cube root both sides. So y equals the cube root of 1 over negative 1/3, 1 plus 3t squared to the 3/2 plus c. And then I'm going to plug in the initial condition to figure out what c is. First, I can do one quick simplification. the cube root of the numerator is 1. So this is 1 over the cube root of negative 1/3 Okay, so then y of 1, I'm going to make all my t's 1, like this one right here. That's the only one. Make that t a 1, and let's see what we get. So I have 1 over the cube root. So 3 times 1 squared is 3, plus 1 is 4. The square root of 4 is 2. 2 cubed is 8, so I have negative 1/3 times 8 plus c, which would be 1 over the cube root of negative 8/3 plus c, and that's supposed to be negative 1. So I just have to solve this. I'm going to multiply both sides by the cube root, so I get 1 equals negative cube root of negative 8/3 plus c, and I'm going to cube both sides. Actually, first I'm going to move the negative to the left. Make things a little bit simpler. Cube, cube. So negative 1 cubed is negative 1 equals negative 8/3 plus c. Negative 1 plus 8/3 is going to be 2/3. Very tempting to just circle this answer. That's right, right? Negative. Oh, nope, that's not right. Okay, that's what I get for trying to do fractions in my head. So negative 1 is negative 3/3, and then you're going to add 8/3 to it, which is 5/3. So again, it's very tempting to circle that as the answer, but that's only a piece of the answer. The answer is the function y equals, and this is what I have for y equals, and I just have to replace the c right here with a 5/3. Okay, next one. We've got a hint partial fractions. First thing I have to do is separate. I need all my y's on one side and my t's on the other. So I'm going to move my 1 minus y squared to the other side by dividing both sides by 1 minus y squared. And so I'm going to have 1 over 1 minus y squared dy, and then I'm multiplying both sides by dt. And then integrate both sides. And to integrate 1 over 1 minus y squared, I need to do partial fractions. So I'm going to do a little aside here where I'm going to try to break this 1 minus y squared into a over 1 minus y plus b over 1 plus y, which is the factorization of the denominator. Then multiply both sides by the common denominator, 1 minus y times 1 plus y. And on the left, everything cancels and you get 1. On the right, the 1 minus y's cancel and you're left with a times 1 plus y. And then when you multiply by the b fraction, the 1 plus y's cancel and you get b times 1 minus y. And then this has to be true for all values of y, so choose some convenient values like y equals negative 1, and you get 1 equals, the a term cancels, and then you have 1 minus negative 1, which is 2. So b is a half. And then if you plug in y equals 1, the b term cancels, and you're left with 1 equals 2a, so a equals a half. So I can change my integral now to be the integral of a over 1 minus y, so 1 half over 1 minus y plus b over 1 plus y, so 1/2 over 1 plus y dy equals t plus c. And then integrating this term by term, you get 1/2 ln of 1 minus y. And then you do need to take into account the chain rule here. If you were to take the derivative of what I just wrote down, we would need to get back to here. But what you would get is 1/2 times 1 over 1 minus y times -1 because of the derivative of the stuff. So I'm going to put a negative in front of this 1/2 to counteract that. Plus 1/2 the ln of 1 plus y. And this one you don't have to worry about the chain rule because the derivative of the stuff inside is 1. Equals t plus c. Okay, so just a little algebra here. I'm going to multiply both sides of the equation by 2. So the right-hand side is going to become 2t. Technically, it's plus 2c, but that's just a new arbitrary constant, so I'm going to write plus c. And then on the left, I'm going to have the ln of 1 plus y minus the ln of 1 minus y. And I can rewrite that as a single logarithm, the ln of 1 plus y over 1 minus y equals 2t plus c. Now solving this for y is going to take quite a bit of algebra. I'm not going to do it for you right now, and I wouldn't ask you to do it. But what I'm going to try to do is plug in the initial condition, y of 0 equals 1, and see if I can figure out what c is. Okay, so if I put in a 0 for my t and a 1 for my y, I get the ln of, if I put in 1 for y, I get a 0 in the denominator. I get 2 over 0. So y can never be 1. Right, so c is undefined. So we found a solution to the differential equation, but there is no point, there is no c that can satisfy this initial condition.